Look up tonight at any galaxy you can find, that faint smudge of 100 billion suns, and understand that almost nothing holding it together is anything you can actually see. The stars are only a thin, bright skin. Underneath them, around them, woven through every one of them is something else, something that gives off no light and has never once been seen, not in nearly 100 years of trying, and there is roughly 5 times more of it than everything that shines. We have only ever felt it, the way you feel a presence in an unlit room. We have never looked upon its shape, and yet somewhere out there, more than 500 million light years away, a giant galaxy hangs in the dark wearing 9 perfect rings of starlight, a target that nobody was ever aiming for, and a handful of physicists have begun to wonder whether those rings are not what they seem. What if the invisible thing has finally left us a portrait of itself? What if, for the very first time, we're not feeling the dark but looking straight at the shape of it? Settle in and get comfortable. Subscribe if you have not, and stay with us, because the question we're about to follow runs from one accidental galaxy all the way to the largest hidden thing in the entire universe. Let's get into it. Part 1. A target. Nobody aimed at. Somewhere in the quiet hours, a graduate student was scrolling through pictures of the sky that nobody had asked him to look at closely. This is how a lot of the universe gets found, by the way. Not with alarms and not with a grand announcement, but with one tired person clicking through image after image of distant smudges, most of them ordinary, most of them already understood, until the eye snags on something that refuses to sit quietly with the rest. He was working through a ground-based survey, the kind of wide, patient sweep of the heavens that catalogues thousands upon thousands of galaxies without comment, and then a single galaxy stopped him cold. It had rings. Not one faint ring, not a smudge that might be a ring if you squinted, but several clean, clear circles nested one inside the other, like something drawn on purpose. He had to stop. He said as much later, in plain words, that he was immediately drawn to it and had to investigate. That is the whole beginning of this story, and I want you to hold on to how small it is, because everything that follows grows out of that one moment of noticing. The galaxy had a name already, the way almost everything in the sky does. A long catalogue label that means nothing to the imagination. Its name was Leader 1313424. You will not remember that, and you do not need to. What you will remember is the nickname the team gave it once they understood what they were looking at, because the nickname is perfect, and it is the reason you are here tonight. They called it the bullseye, and once you see why, you cannot unsee it. Picture the thing you imagine when someone says the word, the target. The concentric rings closing in toward a single point at the center, the pattern that exists in our world for one reason only, to be aimed at. Now hang that pattern in space, blow it up to a scale that makes the mind go quiet, and you have this galaxy. Here is the first strange thing, and we will return to it again and again, because it turns out to be the secret door at the back of the whole mystery. Nobody aimed at the bullseye. It was not the target of the survey. It was not what anyone was hunting. It was found by accident, the way you might find a coin on the sidewalk that turns out to be 200 years old. A target that nobody aimed at. Keep that phrase somewhere in the back of your mind, because by the end of tonight it is going to mean something very different than it means right now, and the distance between those two meanings is, in a way, the whole point. There is something almost poetic in the fact that the most ordered object many astronomers had ever seen was found in the least ordered way imaginable by chance in the corner of a survey aimed elsewhere. The universe is mostly disorder, mostly scatter, mostly the slow random tumble of matter under gravity. Order, real order, clean repeated geometric order, is precious and rare out there, and when it appears it almost always means something is enforcing it. Some rule or structure underneath holding the pattern in place. A snowflake is ordered because the molecules of water can only stack in certain ways. A spiral shell is ordered because growth follows a mathematical law. So when you find 9 clean concentric rings hanging in space, the very orderliness is a clue, a sign that something is keeping time, something is enforcing the spacing. The astronomers did not yet know what, but they knew, the moment they really looked, that they were not staring at an accident. They were staring at the visible result of some hidden rule. And the whole of tonight's journey is really an attempt to name that rule, to figure out what underneath the bullseye is keeping its rings in such perfect order. The first answer everyone reached for was a collision. The second answer, the one we are slowly walking toward, is something far stranger and far larger than any collision could ever be. Now, you might reasonably ask what is so special about a galaxy with rings. Galaxies come in all sorts of shapes. We have the great pinwheels, the spirals with their lazy curving arms. We have the smooth, featureless ellipticals, the old quiet ones, like cities that have stopped growing. We have the ragged irregulars, galaxies that look as if they were assembled in a hurry and never tidied up. Rings, though, are something else. A galaxy with a ring around it is genuinely rare, and a galaxy that is essentially nothing but rings is rarer still, the kind of object you might find a handful of in a sky full of them. So when this one turned up with not one ring but a whole nested set of them, the astronomer who found it was not looking at a curiosity. He was looking at something that, as far as anyone could tell, had no business existing in the form it did. I want to be honest with you from the very start about what kind of story this is, because it is not the kind we usually tell. Most of the time, when we sit down together to look at something out there in the universe, the shape of the evening is a mystery that gets solved. We find a strange object, we are puzzled by it, the scientists work it out, and by the end we understand. Tonight is not that. Tonight is a story where the mystery seems to get solved, cleanly and beautifully, and then, years later, somebody looks at the same picture, runs a few numbers, and quietly suggests that the solution we all accepted might be hiding something far larger underneath it. Something we have never seen. Something that makes up most of the universe, and that we have only ever felt, never looked at directly, not once in nearly 100 years of trying. And the suggestion on the table is that this one galaxy, this accidental bullseye, might be the first place where we are not feeling that hidden thing through its gravity, but actually seeing its shape, drawn out in starlight, for our eyes to count. That is a big claim, and I'm going to spend the next while earning it slowly, the way these things should be earned, one ring at a time. I am not going to tell you it is true. By the end you will understand exactly why it might be, and exactly why it might not, and you will be left, as I am, sitting with a question rather than an answer. But that question is one of the most beautiful I have come across in a long while, and I think it is worth the whole journey. So let us begin where the astronomers began, with the simple fact of the thing. A galaxy, found by chance, ringed not once but many times over, hanging in the dark at a distance that is going to bend your sense of scale before we are even properly underway. Before we ask what made the rings, before we get anywhere near the strange and quiet idea waiting at the end of this, we should just look at it. We should let it be what it first was to the person who found it, an image on a screen that was too orderly, too deliberate, too much like a target to belong to the random sprawl of everything around it. Because the universe, for the most part, does not draw clean circles. It draws chaos and lets gravity slowly comb it into rough order over billions of years. Clean concentric rings are not its native handwriting, and when you find them, the only honest response is the one that astronomer had. You stop, you look closer, you ask what on earth, or rather what far from Earth, could possibly have drawn this, and the moment you ask that question seriously, the floor begins, very gently, to tilt. I think it is worth pausing on how often this is the real shape of discovery, because we are taught a different story. We are taught that science advances when someone sets out to answer a question, designs the perfect experiment and marches toward the result. And sometimes it does happen that way, but just as often, maybe more often, the universe ambushes us. Someone is looking for one thing and notices another out of the corner of the eye. Someone is doing routine work, cataloguing, checking, sorting, and a single entry refuses to behave. The history of astronomy in particular is a long parade of accidents that turned out to matter, of objects nobody was hunting that rewrote the textbooks once somebody bothered to stop and stare. There is a humility in that, and a kind of comfort too. It means the universe is still full of things we have not thought to look for, still leaving its strangest treasures lying in plain sight, waiting for a tired person at a late hour to slow down long enough to see them. What makes the bullseye such a good example of this is that it did not need any special instrument to first announce itself. It was not buried in some exotic kind of light that only one telescope in the world can gather. It was sitting there in an ordinary survey, the kind that produces images by the tens of thousands, the kind that mostly gets processed by software and skimmed by eyes that have seen 10,000 galaxies already and learned to keep moving. The thing that found the bullseye was not a machine, it was attention, a human being deciding that this one was worth stopping for. And everything we are about to explore, the rings, the collision, the impossible speeds, the invisible majority of the universe, all of it flows downstream from that single small decision to pay attention to a target nobody had aimed at. Part 2. 9 Rings, Where There Should Be One. Once the bullseye had been noticed, the next job was to find out how real it was, because the eye is easily fooled and a wide survey from the ground, peering up through the shimmer of our own atmosphere, can blur things together and suggest patterns that fall apart under a sharper look. So the team did what you do when you have found something that might be extraordinary and might be a trick of the light. They pointed the best eyes we have at it. They brought in the Hubble Space Telescope, the great old observatory that has been circling above the atmosphere for more than 3 decades, looking out at the universe without the blur that the air imposes on the rest of us. And they brought in the Keck Observatory in Hawaii, one of the largest ground telescopes on the planet, perched high on a mountain where the air is thin and still. Between them, these instruments could settle the question of how many rings the bullseye truly had and whether they were as clean as they first appeared. The answer, when it came, was almost hard to believe. Hubble's sharp vision picked out and confirmed 8 separate rings, each one a real, distinct circle of stars and gas, pinned down and counted. Then the Keck data confirmed a 9th, fainter and further out, that brought the total to a number no galaxy had ever shown us before. 9 rings. I want you to sit with that, because the number on its own does not land until you know what it is being compared to. Ring galaxies, the rare ones that have any rings at all, almost always have just one. A few, the real oddities, manage 2. A genuine handful in all our catalogues have ever shown 3. And here was a single galaxy carrying 9, 6 more than the previous record holder, more rings than any telescope had ever found around anything, anywhere. It was not a small step past the record. It was a leap so large that it changed what the record even meant. And the astronomers suspected the true number was higher still. Looking carefully at the spacing of the rings, the way they sat nested inside one another, the team came to believe there had once been a 10th ring, even further out than the widest one Hubble could see, that had simply faded over time until it dropped below the level our instruments can detect. They even estimated where it would have been, roughly 3 times farther from the centre than the outermost ring still visible. So the honest count is 9 that we can see, and very likely a 10th that has slipped away into the dark. A galaxy that wears its history in circles and has worn more of them than it shows us now. Then there is the size, and this is where I need you to take a slow breath, because the scale of the bullseye is not the scale of a normal galaxy. Our own Milky Way, the great wheel of several 100 billion stars that we live inside, the one whose faint band you can see arching across a dark country sky, measures somewhere around 100,000 light-years from one edge to the other. That is already a number that does not really fit inside a human head. Light, the fastest thing there is, the thing that crosses from the moon to your eye in a little over a second, takes 100,000 years just to cross our galaxy from side to side. The bullseye is 2.5 times wider than that, roughly 250,000 light-years across. If you could somehow set our Milky Way down beside it, our entire galaxy, everything we know, every star anyone has ever named, would be a coin laid on a dinner plate. This is a giant, and it is wearing 9 rings, and it is far. The light that Hubble gathered to make this image left the bullseye around 551 million years ago. Let me put that in terms of our own world, because the number is too clean to feel. 551 million years ago on Earth, there were no dinosaurs, not for hundreds of millions of years yet. There were no trees, no flowers, nothing walking on land at all. Life was almost entirely in the oceans, soft, strange things only just beginning to invent hard bodies. The light now arriving in our telescopes, the light carrying the picture of those 9 rings, set out across the emptiness when the most advanced thing on this planet was something soft drifting in a shallow sea. It has been travelling that entire time, all those hundreds of millions of years, just to land on a mirror above our heads and tell us this one galaxy has too many rings. There is something almost unbearably patient about that, and I think it is worth feeling before we go on. When the astronomers looked at how the rings were arranged, they found another detail that is going to matter a great deal later. So let me plant it now, and we will come back for it. The rings are not spaced evenly. They are not like the painted circles on an actual dartboard, each one the same distance from the next. Instead, seen face on, they would bunch up tightly near the centre and then spread farther and farther apart as they move outward, a specific particular pattern of spacing. Now, that might sound like a small technical point, the kind of thing only a specialist would care about, but hold on to it, because that exact pattern, the way those rings are spaced, is the thread that one physicist is eventually going to pull, and when he pulls it, the whole comfortable explanation is going to start to unravel. For now, just know that the rings have a rhythm to them, a particular mathematical spacing, and that the universe does not hand out particular mathematical spacings for no reason. I want to dwell a little longer on the number itself, on 9, because I think we move past it too easily. When you hear that a galaxy has 9 rings instead of 1, your mind files it as a bigger version of the same thing, the way 9 apples is just more apples than 1 apple. But that is not the right way to feel it. Going from 1 ring to 9 is not a difference of quantity. It is very possibly a difference of kind. A single ring, or 2, can be made by a single event, 1 collision, 1 disturbance, 1 stone in 1 pond. But 9 clean, separate, sharply defined rings, each at its own carefully spaced distance, is a far harder thing to produce by accident. It is the difference between a single splash and an orderly series of waves marching outward in perfect step. 1 splash is easy. A perfectly ordered series is the kind of thing that makes you wonder whether something underneath is organizing it. Some rule, some structure, some hand-keeping time. The astronomers who found the bullseye knew they were not looking at a slightly more impressive version of an ordinary ring galaxy. They were looking at the most extreme example of the phenomenon ever found, by a margin so wide that it sat in a category of its own. And there is one more thing about the scale of this galaxy that I cannot let pass without comment, because it changes how you should picture the whole event. We tend to imagine collisions as fast and violent, over in a flash, because that is what collisions are like in our world, a car crash, a shattered glass, a moment of impact and then stillness. But on the scale of a galaxy 250,000 light-years across, nothing is fast. The little galaxy that punched through the bullseye did not do it in an instant. Even moving at the tremendous speeds galaxies reach, it would have taken something on the order of millions of years simply to pass through the body of the larger galaxy from one side to the other. The whole catastrophe, the entire impact that may have drawn these rings, unfolded with a slowness that no human life could ever perceive. A collision so enormous and so unhurried that to anything living inside it, nothing would have seemed to be happening at all. The stars of the bullseye did not feel a crash. They felt at most a slow and ghostly tide rising and passing through their neighbourhood over a span of time longer than our entire species has existed. Keep that pace in mind, that immensity of time, because it is going to matter enormously when we start asking how fast the rings could possibly have moved. So this is what the astronomers were holding once the great telescopes had spoken. A galaxy 2.5 times the size of our own, hanging more than 500 million light-years away, wearing 9 clean concentric rings with a 10th that had faded, the rings spaced in a precise and deliberate-looking pattern, the whole thing found completely by accident in a survey that was looking for nothing in particular. It was by any measure one of the strangest and most beautiful objects discovered in years, and the very first question, the one that any of us would ask standing in front of that image, is the obvious one. What could possibly draw 9 rings around a galaxy? What does that to something 250,000 light-years wide? For a while, the answer seemed wonderfully clear. In fact, it seemed like one of the cleanest answers in all of astronomy, an old prediction coming true before the scientists' eyes. And that clean answer is where we go next, because you have to understand how convincing it was before you can understand why somebody dared to doubt it. Part 3. The Arrow and the Pond. To understand how the astronomers explained the bullseye, you do not need any physics at all. You just need a pond and a stone. Picture a still pond on a windless evening, the surface flat and dark holding the last light of the sky. Now drop a stone into the middle of it. You know exactly what happens. You have seen it 1,000 times. A ring spreads outward from the point where the stone went in, and behind it another, and another, a set of circles racing away from the centre, evenly chasing one another toward the shore. That is the picture the astronomers reached for, and it is the right picture, because the mathematics of ripples spreading on a pond and the mathematics of rings spreading through a galaxy are in their bones, the same kind of thing. A disturbance happens at a point, and waves carry it outward in circles. So what was the stone, in the case of the bullseye? The answer was sitting right there in the image, just off to one side of the Great Ringed Galaxy. There was a second, much smaller galaxy nearby, a little blue dwarf, a modest huddle of young hot stars. And the astronomers came to understand that this small galaxy was the culprit. Sometime in the past, this little blue dwarf had not merely drifted near the bullseye, the way galaxies often pass one another in a long, slow, gravitational dance. It had gone straight through it. It had passed like an arrow directly through the centre of the much larger galaxy, punched clean through the core and come out the other side. And that direct central hit is the rarest kind of galactic encounter there is. Galaxies brush past each other all the time on the enormous clock of the cosmos. They sideswipe, they tug at one another, they sometimes merge over billions of years. But for one galaxy to score a direct hit through the dead centre of another, like an arrow finding the exact middle of a target, is extraordinarily uncommon. The bullseye had been shot straight through the middle. The timing they worked out was about 50 million years ago. On the cosmic clock, that is recent, practically yesterday. And when that little galaxy plunged through the centre of the great disk of stars and gas, it did exactly what the stone does to the pond. It sent waves of disturbance racing outward through the larger galaxy. Now, in a galaxy, the waves are not waves of water. They are waves of gravity and density, regions where the passing intruder's pull squeezed the gas and dust together as the ripple moved through. And when you squeeze the gas in a galaxy, something wonderful happens. You trigger the birth of stars. Compressed gas collapses and ignites, lighting up in bright young blue stars, the hot, fast-burning kind, and so each ripple as it spreads lights itself up as a glowing ring of brand new stars. The rings of the bullseye in this picture are waves of star formation, frozen mid-spread, each one marking where the gravitational ripple from that ancient impact had reached. And the evidence fit beautifully. There was the little blue dwarf, the arrow, right where it should be, having continued on its way after passing through. The two galaxies are now separated by about 130,000 light-years, the small one drifting away from the scene of the collision. And there was even a thin trail of gas stretching between them, a faint bridge connecting the great ringed galaxy to its tiny attacker, like a thread of smoke still hanging in the air to mark the path a bullet took. The smoking trail pointed right back along the line of the impact. If you were a detective arriving at the scene, you would have your weapon, you would have its path, and you would have the wound. The case looked closed. But here is the part that makes this more than just a satisfying explanation, the part that turned the bullseye from a curiosity into a small triumph. There was already a theory, worked out by physicists long before this galaxy was ever found, that predicted exactly how the rings from such a collision should behave, how fast they should move outward, how they should be spaced, how they should evolve over time. This theory had been sitting on the shelf for years, a piece of careful mathematics waiting for a galaxy clear enough to test it on. And when the team measured the bullseye's rings and compared them to what the old theory predicted, they matched. Not roughly, not in the general ballpark. One of the researchers described it as almost a one-to-one match with the prediction. His colleague put it in words I find genuinely touching, that the theory had been developed for the day that someone finally saw so many rings, and that it was deeply gratifying to confirm a long-standing prediction with this galaxy. Do you hear what that means? Someone years ago did the math for a galaxy that did not yet exist in anyone's catalogue, predicted how its rings would look, and then the bullseye turned up and wore those predictions like a fitted coat. This is science at its most satisfying. A strange object appears, an old theory rises to meet it, and the two shake hands. The discoverers were not puzzled by the bullseye. They were delighted by it. To them, it was not a mystery at all, it was a confirmation, a clean and rare and beautiful example of collisional ring physics caught in the brief window when all its rings are still visible at once. And they were right to feel that way, because as far as the standard picture goes, everything checks out. The arrow, the pond, the ripples, the new stars, the matching prediction. If the story ended here, it would be a good story, the story of a galaxy that proved a theory right. But I told you at the start that this was the other kind of story. And the thing about a coat that fits perfectly is that you do not look too closely at the seams. For a few years, nobody did. The bullseye sat in the textbooks and the press releases as a solved and lovely thing, the galaxy with 9 rings explained. Ripples in a pond. Remember that phrase, ripples in a pond, because it is about to do a great deal of work and not the work you would expect. It is the comfortable answer, the one we all accepted, the stone and the still water, and it is going to take someone willing to look very closely at the seams, someone who has spent an entire career thinking about a completely different and far stranger part of the universe, to walk up to this beautiful fitted coat and gently ask whether the thing wearing it is really what we think it is. But before we let that happen, I want to make sure I have been fair to the collision story, because it is genuinely good, and the temptation in a story like this is to set up the comfortable answer only to knock it down, and that is not honest. So let me say plainly what the collision model gets right, all the things it explains without breaking a sweat. It explains why the rings are made of young, hot blue stars rather than old ones, because the compression of gas in a passing wave triggers exactly that kind of fresh, fast star formation. It explains why the rings are roughly circular, because a disturbance spreading from a central point naturally spreads in circles. It explains the presence of the little blue dwarf and the gas trail, because a galaxy that just punched through another would indeed be flying away with a thread of stripped gas trailing behind it. And it explains, most impressively of all, why the rings appear at all in this brief moment of cosmic time, because there is only a narrow window after such an impact when so many rings would be visible at once before they fade and spread and vanish. We happen to be looking at the bullseye during that window. The collision model is not a lazy guess. It is a careful, well-supported explanation that accounts for nearly everything we see, and that is precisely what makes the doubt that follows so interesting. It is easy to overturn a bad theory. Bad theories fall over on their own. What is hard and what is rare and what is genuinely thrilling to watch is when someone takes aim at a good theory, a theory that explains nearly everything, that the experts who found the object themselves believe, and finds the one or two threads that, when pulled, will not come loose no matter how hard the comfortable story tugs. The collision model explains the colour of the rings, their shape, the culprit, the timing window, the match to old predictions. It explains everything except, perhaps, the one thing that turns out to matter most, which is how the outermost ring could possibly be where it is. And to see why that one loose thread is enough to call the whole garment into question, we first have to understand the man who pulled it, and the lifelong obsession that taught him to look at rings and see something nobody else was looking for. Part 4. The Lineage of Rings. Before we let anyone doubt the comfortable answer, we owe it to the comfortable answer to understand where it came from, because it did not appear out of nowhere for the bullseye. The idea that a collision makes rings has a long history, and that history is part of why it feels so solid. The first ring galaxy ever recognized was found back in 1941. Astronomers came across a galaxy that appeared to be wrapped in a luminous circle, a bright loop with seemingly empty space between it and the center, and they could not at first explain why. It became known as the cartwheel, and you can guess from the name exactly what it looked like, a great wheel with a rim, and faintly, the suggestion of spokes. The cartwheel was the pioneer, the first of its kind, and over the decades that followed, astronomers gradually found more galaxies like it, more rings scattered across the sky. Most of them had a single ring, some had two, a precious few had three. And slowly the explanation took shape. The same one applied to the bullseye. These rings, the astronomers reasoned, appear when a smaller galaxy strikes through the center of a larger one, sending density waves spreading outward, lighting up circles of new stars as they go. The collision idea was not invented for the bullseye. It was a mature, well-tested explanation, built up patiently over 80 years of finding ringed galaxies and working out what they had in common. The cartwheel itself is worth picturing, because it shows the collision idea at its most convincing. It is a galaxy with a bright outer ring of intense fresh star formation, blazing with young blue stars, and a quieter inner region, with faint spoke-like streamers reaching between them, which is exactly why it earned the name of a wheel. And when astronomers studied it, they did not have to guess at the cause, because there were smaller galaxies nearby, the likely culprits, the bodies that had plunged through and set the rim ringing. The cartwheel became the model case, the picture in the textbook, the proof that a galaxy passing through the center of another really can light up its rim in a ring of new stars. Every ring galaxy found afterward was measured against it. So you can understand why, when the bullseye appeared, the instinct was immediate and reasonable. Here is another ring galaxy, only more so, with 9 rings instead of 1, and there is the little blue dwarf right beside it, the obvious arrow. Of course it is a collision. It is the most natural reading in the world, and it sits at the end of 8 decades of successful reasoning. But notice what the cartwheel and most of its cousins always had that made the collision story so easy to believe. They had a visible culprit and usually just 1 or 2 rings, the modest number you would expect from a single clean impact. The bullseye matches on the culprit but breaks badly on the number. One impact making 1 or 2 rings is the comfortable, well-documented norm. One impact making 9 sharply defined rings, with a 10th that has faded spaced in a precise mathematical sequence, is asking a single event to do something we have never clearly seen a single event do. So even within the collision picture, the bullseye is already an outlier, already straining the model that explains its gentler cousin so well. And outliers, the cases that push a theory to its limit, are exactly where new physics tends to hide, if it is hiding anywhere. And for most ring galaxies, this explanation works wonderfully, because we can often see the evidence with our own eyes. We can find the culprit. When a galaxy has a ring, we frequently spot the smaller galaxy somewhere in the neighbourhood. The one that did the deed, sometimes still close by, sometimes caught in the act of pulling away. The collision picture earns its keep over and over, because the weapon is so often still at the scene. So when the bullseye turned up with its blue dwarf sitting right there, and a gas trail pointing back along the path of impact, it slotted neatly into a story that astronomers had every reason to trust. This was not a wild guess. It was the natural conclusion of a long and successful line of reasoning. But every long and successful line of reasoning has its awkward exceptions, the cases that never quite fit, the ones that get mentioned in a footnote and then politely set aside. And the collision story has one famous, beautiful, deeply uncomfortable exception that has been bothering astronomers since 1950. I want to take you there for a moment, because it is the first hairline crack in the floor, and you should feel it underfoot before we go any further. I want you to imagine you are standing at the edge of a particular galaxy, one discovered in 1950 and named for the astronomer who found it. It is called Hoag's object, and it is one of the most perfect things in the sky. At the centre, there is a tight ball of old yellow stars, calm and ancient, glowing the warm colour of a sun late in its life. Around that core, set well apart from it, there is a flawless ring of brilliant blue stars, young and hot and fast-burning, a circle so clean and so complete that it looks less like a galaxy and more like a piece of jewellery, a golden bead held inside a band of blue fire. And between the core and the ring, in the gap where you are now standing in your imagination, there is nothing. A clean, dark band of empty space separating the old centre from the young ring. Turn slowly, all the way around. Look out along the ring, look back at the quiet golden core. Look into the darkness of the gap you stand in. Now ask the question the whole evening turns on. If a ring like this is made by a collision, by an arrow punching through the centre, then where is the arrow? Where is the small galaxy that did this? Look in every direction. There is none. No culprit nearby. No second galaxy fleeing the scene. No gas trail pointing home. There is just a perfect ring, an old core, and a silence where the cause is supposed to be. A ring with no bullet, and it has been hanging there, quietly refusing to be explained for as long as we have known about it. Now, astronomers are careful people, and Hoag's object did not overturn anything. One strange exception is not a revolution. There were possible answers, ways the ring might have formed without a recent collision, and the object was filed away as a rare oddity, a puzzle for another day. But here is what I want you to carry forward out of this part. The collision explanation, as powerful and as well-earned as it is, has always had a quiet problem sitting underneath it. There has always been at least one ring that no bullet could account for. So when we say the bullseye is explained by a collision, we are standing on ground that is mostly solid but has one known soft spot, one place where the floor has always been a little thin. For most galaxies, that soft spot does not matter, because the culprit is right there. But it means that the door to another kind of explanation has never been fully closed. It has been sitting slightly ajar since 1950, with Hoag's object holding it open. And all it would take to swing that door wide is a galaxy where the collision story, despite having a culprit, despite having a gas trail, despite matching the old predictions, turned out to have a number in it that simply could not be made to work. A galaxy where the arithmetic of the pond broke down. As it happens, that is exactly the galaxy we have been talking about all along. I want to linger one more moment in that dark gap inside Hoag's object. because it teaches something that goes beyond ring galaxies, something about how science actually carries its unsolved problems. We did not throw out the collision theory when we found a ring with no bullet. We did not announce a crisis. We did something far more human and far more useful. We held the strange case gently to one side, acknowledged that it did not fit, and kept using the theory everywhere it did fit, which was nearly everywhere. That is not a flaw in how science works. That is the wisdom of it. A good theory earns the right to have a few exceptions parked at its edges, problems we cannot yet solve but choose not to let paralyze us. The danger is only this, that over enough years the parked exceptions can fade into the background, become invisible through familiarity, until we forget they are exceptions at all and start to feel that the theory explains everything. The mark of a careful scientist is someone who never quite forgets the parked cases, who keeps one eye on the soft spot in the floor even while walking confidently across the solid part. Pierre Sikivi is that kind of scientist, and the soft spot he never forgot was the possibility that some rings are not made by collisions at all. So when we say the door to another explanation has been ajar since 1950, what we really mean is that there has always been a small, stubborn group of physicists who looked at ring galaxies and wondered whether the universe might be drawing some of those circles by a mechanism we had not properly considered, a mechanism involving the invisible part of the cosmos rather than the visible. For most of those years, they had no clear case to point to, no single galaxy where the collision story so plainly failed that it forced the question into the open. They had only Hoag's object and a handful of other oddities, suggestive but never decisive. What they were waiting for, though they could not have said so, was a galaxy with rings so numerous, so sharp and so impossibly placed that the comfortable answer would visibly strain and crack under the weight of its own numbers. They were waiting, in other words, for the bullseye, and the thing that finally cracked the comfortable answer was not a philosophical objection or a matter of taste. It was a single, stubborn, undeniable number. Part 5. The crack widens. The person who looked closely at the seams was not a galaxy specialist chasing ring galaxies. He was a physicist who has spent a large part of his career thinking about the part of the universe we cannot see at all, and we will get to that in a moment, because it is the centre of everything tonight. His name is Pierre Sikivi, and along with his colleague Yuxin Zhao at the University of Florida, he did something very simple and very dangerous to a beautiful theory. He took the collision explanation at its word, and then he checked whether the numbers actually added up. Not the general shape of the story, which is lovely, but the hard arithmetic underneath it. And what he found is the kind of thing that, once you see it, you cannot look away from. Here is the problem, and you can follow every step of it without any mathematics. We said the collision happened about 50 million years ago. That is the clock. We also know how far out the rings extend because we can measure them, and the outermost ring sits a very long way from the centre of that enormous galaxy. So now you have a simple question, the kind you could ask about a car on a highway. If the outermost ring started at the centre 50 million years ago, and it is now all the way out at the edge, how fast did it have to travel to get there in that time? Distance divided by time. That is all. And when Sikivi and Zhao did that division, the answer that came back was about 1,220 kilometres every second. Let me say that again so it lands. To reach where it is now in the time available, the outer ring would have had to race outward at over 1,200 kilometres per second, which is more than 750 miles every single second. That number is a problem, and to feel why, you need something to compare it to. In our own Milky Way, there are stars that have been flung outward at tremendous speeds, the so-called hypervelocity stars, slingshotted by violent encounters near the galaxy's centre until they are screaming out toward intergalactic space. Those are the fastest large things we know of inside a galaxy, and the ring of the bullseye on the collision clock would have to be moving faster than they do. But ring waves are not supposed to be hypervelocity anything. The kind of density wave that spreads from a galactic collision, the ripple in the pond, is expected to move outward slowly, gently, on the order of a few tens of kilometres per second. That is the natural pace of the disturbance. So we have a prediction of something slow, on the order of perhaps 50 kilometres per second, and we have a requirement, if the collision clock is right, of something more than 1,200. That is not a small disagreement. That is a mismatch by a factor of around 20. The ring is in the wrong place for its age, by an enormous margin, if ripples in a pond are really what made it. And there is a second problem, quieter, but just as troubling. Think again about the pond. When you drop the stone and the ripples spread, what happens to them as they travel? They soften, they blur, they begin to overlap and smear into one another, losing their crisp edges the farther they get from the centre and the longer they have been travelling. Ripples that have been spreading for tens of millions of years should, by the collision picture, be getting fuzzy, bleeding into each other, losing definition. But the rings of the bullseye are not fuzzy. They are remarkably sharp, remarkably distinct, clean enough that Hubble could count them one by one from 500 million light-years away. The rings are too crisp for their age, just as the outer one is too far for its age. Two different measurements, two different ways in which the comfortable answer quietly fails to fit. Let me put that speed in human terms, because 1,200 kilometers per second is one of those numbers that is so large it stops meaning anything, and I want it to mean something. At that speed, you would cross the entire United States coast to coast in about 4 seconds. You would travel from the Earth to the Moon in a little over 5 minutes, the fastest rocket humanity has ever launched. Our quickest probe screaming away from the Sun moves at a small fraction of that pace. And we are not talking about a tiny spacecraft. We are talking about an entire ring of stars and gas, an enormous circular structure spanning a good portion of a galaxy, supposedly racing outward as a body at more than 1,000 kilometers every second. Density waves, the gentle ripples that collisions actually produce, do not do that. They cannot do that. They are slow, patient disturbances, the cosmic equivalent of the swell that spreads lazily across a pond, not a shock wave tearing outward at 0.1% of the speed of light. So when Sikivi and Zhao laid the simple arithmetic on the table, distance over time, and the answer came back larger than anything ring physics allows, they were not nitpicking. They had found the place where the comfortable story asks you to believe something the comfortable story itself says is impossible. And remember, this is not a problem you can fix by simply saying the collision was older, giving the ring more time to crawl out, because pushing the collision further back into the past creates its own troubles. If the impact happened much longer ago, then the rings would have had far more time to spread, soften, and blur into one another, and we are right back to the sharpness problem, the fact that these rings are knife-clean rather than smeared. The two problems work against each other. Make the collision recent enough to keep the ring sharp, and the outer ring has to move impossibly fast. Make it old enough to let the outer ring travel at a believable speed, and the rings should have blurred away long ago. The collision story is caught in a vice of its own numbers, squeezed from both sides at once. There may yet be some clever way out, some richer model that escapes the vice, and people are working on exactly that. But the vice is real, and it is what gave a dark matter physicist the opening to suggest that the rings were never travelling at all. So now stand back and feel what has happened. The phrase we have been carrying, ripples in a pond, was the whole comfortable explanation. The stone, the spreading circles, the matching old prediction. And here is the trouble. The pond cannot ripple that fast. Whatever made the outer ring of the bullseye, it was not a gentle wave of compression spreading at the leisurely pace that gravity allows. Something put a ring out there at a distance that a 50-million-year-old ripple has no way to reach, and it put it there sharp and clean rather than soft and smeared. The solved mystery is, very quietly, unsolving itself in front of us. Now, I want to be careful and fair here, because there are ways the collision camp could push back, and an honest account has to mention them. Perhaps the timing is wrong, and the collision happened longer ago than 50 million years, which would give the ring more time to travel and lower the speed it needed. Perhaps the geometry is more complicated than a simple ripple, with the rings forming and moving in ways the basic picture does not capture. These are real possibilities, and the question is genuinely still being worked out by people far more expert than any quick summary can convey. I am not telling you the collision model is dead. I am telling you that a serious problem has been placed on the table, a number that does not want to behave, and that this number was enough to make a respected physicist propose that we may have been reading the whole galaxy wrong. Because here is the thing about that outer ring. It is not a minor detail off in the corner of the image. It is the largest, the most distant, the most extreme of all the rings, and any explanation of the bullseye has to account for it. You cannot simply ignore the ring that breaks your model and keep the 8 that fit. If the outermost ring is in a place that ripples cannot reach in the time available, then either the time is wrong or the ripples are wrong, or the rings were never ripples to begin with. And once you allow yourself to seriously entertain that last possibility, that the rings were never spreading waves of gas at all, a strange and wonderful door swings open. Because if the rings are not moving outward, if they are not waves at all but something more like a standing pattern, a fixed structure that the visible matter has settled into, then the impossible speed problem simply evaporates. There is no speed problem if nothing has to travel. The ring does not need to race anywhere at 1,200 kilometers per second if it has been sitting quietly at that radius all along, held in place by something underneath it. And what could hold a ring of stars and gas in place across that span, invisibly, from below? Only one candidate in all of physics has the mass and the reach to do such a thing, and it is the same thing we have never seen. And the man who noticed this was not content to simply point out the problem and walk away. He had a different idea about what those rings might be, an idea he had in fact been carrying for decades, long before this galaxy was ever found. To understand it, we have to leave the bullseye behind for a while and go looking for the largest missing thing in all of science, the thing that makes up most of the universe and that no one has ever seen. Because Sikivi's whole career has been spent thinking about it, and his suggestion is that the rings of the bullseye are not ripples in gas at all. They are the shape of the dark. Part 6. The Thing That Isn't There. Let me tell you about the strangest fact in all of astronomy, a fact so strange that we have somehow gotten used to it, which is itself a little alarming. Almost everything in the universe is made of something that no one has ever seen. Not seen with the eye, not seen with any telescope, not caught in any laboratory, not touched, not held, not directly detected even once in nearly a century of trying. We know it is there. We are as sure it is there as we are sure of almost anything in science, and we have no idea what it is. We call it dark matter, and the name is almost an apology, a placeholder, a way of giving a label to our own ignorance. It does not mean matter that is a dark colour. It means matter that gives off no light at all, that does not shine and does not block light, that drifts through everything and announces itself in only one way, through the pull of its gravity. Here is how we came to know about it, because the story matters and the people in it matter. Back in the 1930s, an astronomer named Fritz Zwicky was studying a great cluster of galaxies, hundreds of galaxies bound together by gravity, all swarming around one another like bees around a hive, and he measured how fast they were moving, and he got a result that made no sense. The galaxies were moving far too quickly. They were rushing around so fast that the gravity of all the visible matter in the cluster, all the stars and gas he could see, should not have been nearly enough to hold them together. By every calculation, that cluster should have flung itself apart long ago, the galaxies scattering off into the dark like a crowd with nothing to hold it. And yet there it was, intact, held. Zwicky concluded that there must be a great deal of matter in that cluster that he could not see, some unseen mass providing the extra gravity needed to keep the whole thing bound. He gave it a name in his own language. He called it the dark matter. And for a while, the idea sat at the edge of astronomy, too strange to embrace, too stubborn to dismiss. Then, in the 1970s, an astronomer named Vera Rubin made the case impossible to ignore. She studied the way individual galaxies spin, measuring how fast the stars in the outer regions were circling compared to the stars near the centre. And she expected the outer stars to move more slowly, the way the outer planets of our solar system orbit more slowly than the inner ones, because that is what gravity does when most of the mass is concentrated in the middle. But that is not what she found. She found that the outer stars were moving just as fast as the inner ones, racing around the edges of their galaxies at speeds that the visible matter could never explain. It was as if each galaxy were embedded in something much larger and heavier than the part that glows, an unseen reservoir of mass extending far beyond the visible edge, holding those outer stars in their fast orbits. Galaxy after galaxy told the same story. The light we can see is only a small part of what is actually there. What I love about that history is how reluctant everyone was to believe it, and how the evidence won anyway. When Zwicky first suggested unseen mass in the 1930s, the idea was largely set aside for decades, partly because it was so strange and partly because Zwicky himself was a prickly and difficult man who many colleagues preferred not to agree with. The universe did not care about any of that. The missing mass was there whether or not anyone liked the person pointing at it. And when Rubin came along a generation later with her careful, patient measurements of spinning galaxies, measurement after measurement, galaxy after galaxy, the evidence simply accumulated until it could no longer be waved away. This is how science is supposed to work at its best. Not a single dramatic proof, but a slow, grinding weight of observation that eventually becomes too heavy for any amount of discomfort to hold up. By the end, the question was no longer whether dark matter existed. The question became what on earth it could possibly be, and that question is still open today, which is part of why the bullseye matters so much. Let me give you one more way to feel the scale of our ignorance here, because I think it is the thing most worth carrying out of tonight regardless of how the bullseye turns out. Imagine you are handed a complete inventory of everything in the universe, every kind of stuff there is, sorted by how much of it exists. Near the bottom of that list, a small entry would be everything you have ever seen or touched or known. Every star, every planet, every cloud of gas, every living thing, every atom of every object in your home and your body and your world. All of it together, the entire visible cosmos, would account for only a small fraction of the matter, and a smaller fraction still of everything. Above it on the list would sit dark matter, 5 times more abundant, completely unseen. And above even that, a separate mystery for another night, would sit dark energy, more abundant still. We, the visible, are a thin, bright skin stretched over a universe that is overwhelmingly made of things we cannot see and do not understand. We are the rounding error that happens to glow, and against that backdrop, the possibility that one galaxy might let us finally look at the larger, darker part of the inventory, instead of merely inferring it, is not a small thing. It would be like a creature that had only ever felt the ocean through the rocking of its boat suddenly being shown, for the first time, what the water beneath actually looks like. In the decades since, the evidence has only grown, and it has grown overwhelming. We have weighed the unseen matter by watching how it bends the light of more distant galaxies passing behind it, because gravity bends light, and the amount of bending tells you the amount of mass. We have mapped its scaffolding across the whole universe, the great invisible web along which the visible galaxies are strung like dewdrops on a spider's thread. And every measurement, from the smallest galaxy to the largest structure, lands on the same astonishing accounting. For every kilogram of ordinary matter in the universe, the kind that makes up stars and planets and gas and you and me, there are roughly 5 kilograms of this other stuff, this dark matter, that we have never seen. It is not a minor correction. It is most of the matter there is. Around 85% of all the matter in the universe is something we cannot see and do not understand. I want you to stop with me here for a moment, because this is one of those facts that we move past too quickly, and it deserves better. Consider what it actually means. The galaxy you live in, the Milky Way, the great wheel of stars wrapping around you on a dark night, is mostly not the stars. It is mostly this invisible thing, an enormous unseen mass that the stars are merely floating within, like a few bright fish suspended in a body of dark water that goes on far beyond where the light reaches. The thing that holds your galaxy together, the thing that holds you in your slow orbit around its center, the thing that has shaped where every star you can see was born and how it moves, is something no instrument has ever directly touched. You have lived your whole life inside a house, and the walls of that house, the great load-bearing structure that holds the whole thing up, have never once been seen by anyone. We have only ever felt them in the dark by the way everything leans against them. Most of what there is something we have never seen, and the evidence for those unseen walls is not some single shaky measurement that might be explained away. That is what makes dark matter so stubborn and so impossible to wish out of existence. The case comes at us from many independent directions, each one pointing to the same conclusion. There are the spinning galaxies, holding together as if gripped by far more mass than they show. There is the bending of light, because gravity warps the path of light passing near any mass, and when we look at the light of distant galaxies passing behind a great cluster, it is bent far more strongly than the visible matter could ever bend it, telling us there is a tremendous amount of unseen mass doing the bending. There is the way galaxies are arranged across the entire universe, not scattered randomly, but strung along an immense network of filaments and sheets, a cosmic web whose structure simply cannot be built by the gravity of ordinary matter alone within the age of the universe. It needs the extra scaffolding of dark matter to form at all, and there is the faint afterglow of the early universe itself, the oldest light there is, whose pattern carries within it a precise accounting of how much ordinary matter and how much dark matter the cosmos contains. Every one of these is a separate window, looking at a different part of the universe on a different scale, using a different method, and every one of them sees the same thing. There is about 5 times more invisible matter than visible. The conclusion does not rest on a single thread. It rests on a rope woven from many. So when people ask, reasonably, whether dark matter might just be a mistake, a fudge we invented to cover a gap in our understanding of gravity, the honest answer is that some very smart people have tried hard to remove it that way, by changing the laws of gravity instead of adding invisible matter, and those attempts struggle badly against the full sweep of the evidence, especially the bending of light in places where the visible matter and the unseen mass appear to have been physically pulled apart from one another. We have not seen a particle of dark matter. That much is true and important. But not having seen something is very different from that thing not being there. We worked out that an unseen planet was tugging on the orbit of another, long before anyone pointed a telescope at it, and found it exactly where the gravity said it should be. Inference from gravity has a long and honourable record of being right. So we are left in this remarkable position, holding overwhelming evidence that most of the matter in the universe is some unknown substance, and not the faintest direct sight of what that substance actually is. And for nearly 100 years, that has been the frustration, and, if I am honest, the quiet romance of dark matter. It is everywhere. It is most of everything. And it is invisible, known only through its pull, like a presence felt in an empty room. We have built enormous experiments far underground, waiting in silence for a single particle of it to bump into our detectors, and the silence has, so far, held. We have a list of candidates for what it might be, suspects in the greatest missing mass case in history, and we will meet the strangest and most promising of them shortly. But I needed you to feel the size of the thing first, the sheer scale of our not knowing, because it is the backdrop against which the bullseye suddenly becomes something far more than a pretty galaxy with too many rings. If most of the universe is something we have never seen, and if we have only ever felt its gravity and never looked upon its shape, then the most exciting question you could possibly ask is this. Could there be a place, somewhere out there, where the invisible thing finally leaves a mark we can see, where instead of merely feeling it, we could look at a picture and point and say, there, that is the shape of it. Hold that question. We are walking back toward the bullseye now, but we're going to take the long way, through a ghost. Part 7. The Shape. We assumed. When you carry an invisible thing around in your imagination for long enough, you start to give it a shape, even though you have never seen it. We could not help it. For decades, the picture most scientists held of dark matter around a galaxy was a simple one, and it was a sphere. Not a perfect billiard ball sphere, but a great rounded cloud, a halo, an enormous fuzzy ball of unseen matter with the visible galaxy sitting at its centre, like a coin dropped into the middle of a beach ball. The stars and the gas, the part that glows, would be concentrated in a flat disk in the middle, but the dark matter would extend far beyond them in every direction, a roughly spherical fog of invisible mass, densest near the centre and thinning out smoothly toward the edges. We call it the halo, and it is the standard mental image, the one in the textbooks, the one that does its job, and it does its job well, which is exactly why we kept it. That smooth spherical halo explains Vera Rubin's fast-spinning outer stars beautifully. If you wrap a galaxy in a large rounded cloud of extra mass, the outer stars feel that extra gravity and speed up to just the rates she measured. The halo explains how galaxies hold together, how clusters stay bound, how the whole cosmic web hangs in place. For most of what we ask of dark matter, a smooth featureless ball is all you need, and there is a long-standing principle in science that you should not make a thing more complicated than the evidence demands. So the smooth halo stood, comfortable and unchallenged, the assumed shape of the invisible, but notice the word I keep using, assumed. We assumed the halo was smooth because nothing forced us to assume otherwise, not because anyone had ever looked at one and seen that it was featureless. Remember, we have never seen a dark matter halo at all. We have only inferred that it is there and worked out roughly how much of it there must be, and how it must be spread out to produce the gravity we measure. The smoothness was a default, the simplest assumption that fit, not an observation. And there is a great difference between a thing that is smooth and a thing we have merely assumed is smooth because we have never managed to look at it closely. The fog might be featureless, or the fog might have structure inside it, edges, currents, even rings that we have simply never been in a position to detect because we have never had a way to see the dark matter directly. We have only ever felt its total weight, and total weight tells you nothing about shape. A smooth ball and a ball full of hidden structure can weigh exactly the same. This is a subtle point, and it is worth making sure it has fully landed because it is the hinge the whole alternative explanation swings on. Everything we have ever learned about a dark matter halo, we have learned from its gravity, and gravity at a distance mostly tells you about total mass and roughly how it is spread out. It is a blunt instrument for reading shape. Think of it like trying to understand the contents of a wrapped present purely by how heavy it feels and how its weight shifts when you tilt the box. You could tell a heavy gift from a light one, and a top-heavy one from a balanced one, but you could never tell from weight alone whether the thing inside was a smooth ball or an intricate sculpture, as long as the two weighed the same and balanced the same. The wrapping paper of dark matter is its invisibility, and gravity is our only way of feeling through it, and gravity simply cannot resolve fine internal structure from far away. So for all these decades, when we pictured the halo as smooth, we were not reporting an observation. We were drawing the simplest shape consistent with the weight in our hands. The halo could have been smooth. It could also have been threaded with rings and folds and edges, and we would never have known the difference because we have never had a way to unwrap it. What the caustic ring idea offers, then, is not just a new explanation for one galaxy. It offers, in principle, a way to finally read the shape inside the wrapping, by looking not at the dark matter directly, but at the imprint its structure leaves on the visible matter we can see. If dark matter folds into rings, and if those rings gather ordinary gas and stars into matching rings of light, then the light becomes a readout of the hidden structure, a way of unwrapping the present without ever touching the paper. That is an enormous prize, if it is real. It would turn galaxies into instruments for mapping the invisible, and it would mean that the smoothness we assumed for a century was simply the limit of our old way of looking, not a fact about the universe. And it all hinges on whether dark matter is the kind of thing that folds. Which brings us at last to the one candidate that would. This is the crack that Pierre Sacchivi spent his career prying at, long before the bullseye was found. He asked a question that most people did not bother to ask, because the smooth halo was working fine, and there seemed no reason to disturb it. He asked, what if the halo is not smooth? What if, depending on what dark matter actually is, the invisible cloud around a galaxy organizes itself into a definite pattern, with regions where it piles up far denser than its surroundings, arranged not randomly but in a regular, predictable structure? And not just any structure. What if it arranges itself into rings? This was not idle speculation. It came out of taking seriously one particular idea about the nature of dark matter, one specific candidate for what the invisible stuff is made of, and following the logic of that candidate all the way to its strange conclusion. If dark matter is a certain kind of particle, behaving a certain way, then the smooth halo is wrong, and the truth is something with edges and rings hidden inside it. To understand why, we have to meet that particle. It is one of the leading suspects in the whole mystery, and it is about as close to a ghost as anything in physics has ever been. I want to flag something about the move Sacchivi made, because it is the secret engine of a great deal of science, and it is worth seeing clearly. He did not start from the bullseye and reason backward to a cause. He started, decades earlier, from a question about the nature of dark matter, followed the logic of one particular answer to that question, and arrived at a prediction that disk galaxies should carry rings of dark matter in a regular pattern. The prediction came first, sitting on its shelf describing rings that no one had yet found in a substance no one had yet seen. This is the riskiest and most beautiful thing a scientist can do, to commit to a specific consequence of an idea before the evidence exists, to say in advance, if I am right, then one day someone will find a galaxy that looks like this. Most such predictions are never tested in a lifetime. Many are simply wrong. But every so often, the universe produces the very object the prediction described, and a piece of mathematics written years ago in an empty room suddenly has a face to wear. Whether or not the bullseye turns out to be that object, the shape of the reasoning is the same, and it is the shape that has carried physics to its strangest and truest discoveries. You take an idea seriously enough to say what it would mean, out loud, in advance, and then you wait for the sky to answer. And the idea Sacchivi took that seriously, the one that gives the smooth halo edges and rings, depends entirely on what dark matter actually is. Not its weight, which we know, but its nature, which we do not. Different candidates for dark matter would behave in completely different ways. Some would stay a smooth, featureless fog forever. But one candidate in particular, if it is the right one, would do something extraordinary as it falls into a galaxy. It would fold, it would pile up, it would draw rings, and that candidate is the ghost we are about to meet. Part 8. The Ghost Particle. The particle is called the axion, and it has one of the stranger origin stories in physics, because it was not invented to explain dark matter at all. It was proposed to solve a completely different and rather technical problem, a puzzle about why one of the forces of nature behaves with a perfect symmetry that it did not have to have. Physicists, trying to explain that unexpected tidiness, worked out that it could be accounted for if a new particle existed, a very particular kind of particle, extraordinarily light and almost completely standoffish, barely willing to interact with ordinary matter at all. The particle was a side effect, a consequence of fixing an unrelated problem. And only later did people realize that this shy, feather-light particle, if it existed in enormous numbers left over from the early universe, would have exactly the properties you would want from dark matter. It would be invisible, it would barely interact with anything, and there would be a tremendous amount of it. The fix for one problem turned out to be a candidate for the greatest missing mass case in science. I find this one of the loveliest patterns in all of physics, the way a particle proposed to tidy up one small corner of the theory turns out, unexpectedly, to be exactly the thing needed to solve a completely separate and far larger mystery. The original problem the axion was meant to fix had nothing to do with galaxies or missing mass at all. It was a question about why one of the fundamental forces, the strong force that binds the cores of atoms together, behaves with a symmetry that the equations did not require it to have. By all rights, that force could have shown a certain kind of imbalance, and yet when we measure it, the imbalance is absent, exquisitely, suspiciously absent. Physicists do not like unexplained tidiness any more than they like unexplained mess, and so a mechanism was proposed to enforce that tidiness, and the axion fell out of that mechanism as a necessary consequence, a new particle that had to exist if the explanation was correct. It was a creature of pure theoretical housekeeping. And then someone realized that this housekeeping particle, if it existed in the staggering quantities that the early universe would have produced, would drift through the cosmos invisibly, barely interacting, carrying mass, clumping under gravity, doing every single thing dark matter is observed to do. Two mysteries, born in completely different rooms, turned out to have a single answer that fit them both. When that happens, when one idea quietly solves two unrelated problems at once, physicists pay close attention because the universe seems to favour such economies, and ideas with that kind of double payoff have a habit of turning out to be true. None of which proves the axion is real, of course. Plenty of beautiful ideas with double payoffs have turned out to be wrong, and the universe is under no obligation to be elegant. But it is enough to make the axion one of the most seriously pursued candidates for dark matter there is, the focus of careful experiments and the working hypothesis of a great many physicists, and it is the reason a man like Sikivier could spend a career taking the axion seriously enough to work out, in detail, what a universe full of them would look like, right down to the rings such a universe might draw around its galaxies. I want you to appreciate just how slight a thing an axion would be, because its near-nothingness is the whole point. If axions are real, they are almost unimaginably light, far lighter than the familiar particles that make up atoms, so light that a single one carries barely any presence at all. And they are antisocial in the extreme, passing through ordinary matter as though it were not there. Let me put you alongside one just for a moment so you can feel what we're dealing with. Imagine you could shrink your awareness down and ride along with a single axion as it drifts in from the dark cloud surrounding our galaxy. It comes in silently, moving through the outer reaches of the Milky Way, in through the great spiral arms, and it does not bump into anything, because it almost never does. It passes through clouds of gas as if they were open windows. It reaches our solar system, slips past the outer planets without the faintest tug, crosses the orbit of the Earth, and then comes to our world itself, and it does not stop. It passes straight through the planet, through the rock and the iron core, and out the other side, untouched and untouching. It passes through the room you're in. It passes through you, through your skin and your chest, and out again. And you feel nothing, because there is nothing to feel. Right now, if this idea is correct, countless trillions of these ghostly particles are streaming through your body every moment, through the Earth, through everything, a constant silent wind of the invisible, and not one of them so much as nudges a single atom of you. That is the axion. Almost no mass, almost no interaction, almost nothing at all. And yet, gathered together in the staggering numbers that would fill a galaxy, these almost nothings would add up to most of the mass there is, and their gravity would shape the motion of every star you can see. This is why finding one has been so maddeningly hard. For decades, physicists, Sikivi himself prominent among them, have built clever, patient experiments designed to catch the faintest whisper of an axion, to coax one of these ghosts into revealing itself just once. The experiments sit and wait, tuned with exquisite care, listening for a signal so faint it might as well be silence, and so far, that is mostly what they have heard. Silence. Decade after decade of it. The axion remains undetected, a particle that lives, for now, only in the mathematics and in the hope of the people hunting it. I want to be very clear and very honest about this, because it matters enormously for everything that follows. We have never found an axion. We do not know that dark matter is made of axions. It is a candidate, a leading and beautiful candidate, but a candidate still. Everything we are about to build on top of the axion is therefore a structure, standing on a foundation we have not yet confirmed is solid. Keep that in your mind. We are following a possibility, not a fact. But oh, what a possibility it is, because if dark matter is made of these ghosts, and if you follow the rules they would have to obey, you arrive at something that looks remarkably like a galaxy wearing rings. There is something I find quietly moving about the people who hunt for axions, and I want to say a word about them before we move on, because it is easy to talk about particles as if they were abstractions, and forget that real human beings have given their working lives to chasing this one. The axion is not an easy thing to look for. Because it barely interacts with ordinary matter, you cannot simply build a detector and wait for it to crash into something the way you might catch a more sociable particle. You have to be far cleverer than that, coaxing the ghost into revealing itself through subtle and indirect effects, tuning your instrument with painful precision across a whole range of possibilities, because we do not even know the axion's exact mass, only the range it might fall within. So the search becomes a slow, patient sweep, like turning the dial of an old radio with infinite care across a band of static, listening for the faintest hint of a station that may or may not be broadcasting at all. The experiments run for years. They sit in their underground homes shielded from every stray signal, and they listen, and mostly they hear nothing, and the scientists adjust the dial a fraction and listen again. It is one of the most patient forms of hope I know of in all of science. Decades of careful silence, sustained by the belief that the ghost is real, and that one day the dial will land on the right place and the silence will break. And I tell you this not to be sentimental, but because it bears directly on how we should weigh everything that follows. The axion is the foundation under the entire dark matter explanation of the bullseye, and that foundation has not yet been confirmed. If the experiments that have been listening for so long ever do catch their ghost, then the caustic ring idea will stand on solid rock, and the suggestion that the bullseye shows us dark matter's shape will gain enormous weight. But until that day comes, we are following a chain of reasoning whose first link is a particle we believe in, but have never held. That is not a reason to stop following it. The best ideas in physics have often run ahead of the evidence for years before the evidence caught up. It is only a reason to hold the whole structure honestly, as a magnificent possibility rather than a settled fact. With that honesty firmly in hand, let us follow the ghost the rest of the way, and watch how a particle that passes through everything could, against all intuition, draw a ring you can see. Part 9. Caustics. To get from a ghost particle to a ring, you need one more idea, and it is a beautiful one. So let me give it to you with something you can actually see, something you have almost certainly seen without ever knowing it had a name. Take a cup of coffee or any cup of liquid, and set it in sunlight or under a bright lamp. Look down into it. On the surface of the coffee, near one side, you will often notice a bright curved line of light, a glowing curve sharper and more intense than the light around it, shaped a little like a crescent or a pointed curve folded against the rim. That bright curve is called a caustic. It is not a thing floating in the coffee. It is a place. It is the place where a great many rays of light, bouncing off the curved inside of the cup, all happen to fold together and overlap, piling up so that the brightness concentrates along that one curved line. Light is arriving everywhere on the surface, but along the caustic the rays bunch and stack, and so that is where it glows. A caustic is what you get when many paths fold over one another and concentrate in the same place. Now hold that picture, the bright folded curve in the coffee cup, and let me show you how the very same idea, applied not to light but to dark matter, gives you rings around a galaxy. Picture the dark matter not as a static fog but as something flowing, particles drifting inward under the galaxy's gravity, falling toward the centre. A particle falls in, swings around through the inner region, and then, because it has speed, it climbs back out the other side, slows, stops at some farthest point and falls back in again, over and over, like a pendulum swinging through the galaxy. Now here is the key. At the turning points, the places where the falling particles slow to a stop before reversing, they spend more time, and their paths fold over one another, and they pile up. Just like the light rays in the coffee cup, the dark matter particles concentrate wherever their trajectories fold together, and those places of folding and piling up form surfaces of much higher density, sheets and rings where the invisible matter is packed far thicker than anywhere else. They are caustics, exactly the same kind of structure as the bright curve in your cup, but made of dark matter and drawn on the scale of a galaxy. And because a galaxy spins, because the whole system has rotation, there is a rule that organizes these caustics into a particular shape. The rule is the conservation of angular momentum, the same principle that makes a spinning figure skater speed up as she pulls her arms in. That spinning, applied to the infalling dark matter, takes the caustics and arranges them into a set of rings, lying in the plane of the galaxy, nested one inside the other. Not randomly spaced rings either. The mathematics predicts a specific regular pattern of radii, the rings sitting at particular distances from the centre, bunched closer together near the middle and spreading wider toward the edge, in a sequence you can write down and calculate. This is Sikivi's old idea, and I want to stress how old it is. He worked this out decades ago, long before anyone had ever heard of the bullseye. He predicted that if dark matter is the right kind of particle, then disk galaxies should carry caustic rings of dark matter, with a definite and regular pattern of ring radii. It was a prediction sitting on the shelf, waiting, the same way the collision theory had been sitting on its own shelf. A piece of careful mathematics describing rings that no one had yet found, made of a substance no one had yet seen. Let me make sure the caustic idea has really landed, because it is the conceptual centre of the whole evening, and it is the kind of thing that slips away if you only hear it once. The crucial move is to stop thinking of dark matter as a static cloud just sitting there and start thinking of it as something in motion, falling. A dark matter particle, far out in the halo, feels the pull of the galaxy and begins to fall inward. But it does not stop at the centre, any more than a ball dropped into a valley stops at the bottom. It overshoots, climbs the far side, slows, halts at some highest point and falls back, swinging through the galaxy over and over across enormous spans of time. Now picture not one particle doing this, but countless trillions, all falling and rising and falling again. At the turning points, where they slow to a stop before reversing, they linger, they crowd, and critically the paths of many particles fold over one another there, the way a sheet of paper creases when you fold it, creating a surface where the density suddenly spikes far above the smooth average. That crease, that fold of piled up dark matter is the caustic. It is not made of special particles. It is made of ordinary dark matter that all happens to be lingering and folding in the same place at the same time, exactly as the rays of light all happen to fold along the bright curve in the coffee cup, and then the spin does its work. Because the galaxy rotates, the infalling dark matter carries a swirl with it, and that swirl, governed by the unbreakable rule that angular momentum must be conserved, organizes the folds not into random sheets, but into clean, nested, circular rings lying flat in the plane of the galaxy. The mathematics even tells you where the rings should fall, at what radii, in what pattern of spacing, bunched toward the centre and widening outward. So the caustic ring model does not just say there might be rings of dark matter, it says there should be rings, at specific places, in a specific rhythm, if dark matter is the right kind of falling, folding, spinning stuff. That specificity is everything, because a vague prediction can match anything, and therefore proves nothing, while a precise prediction, a particular pattern of radii written down in advance, can either match a real galaxy or fail to, cleanly and honestly. Sikivi had written down a precise pattern. The bullseye had a precise pattern of its own. The only question left was whether the two patterns were the same. Do you feel the two shelves now, sitting side by side? On one shelf, a decades-old theory of collisional rings ripples in a pond, which the bullseye seemed to match so beautifully. On the other shelf, a decades-old theory of dark matter caustic rings, a regular nested pattern pressed into the invisible halo, also waiting for a galaxy clear enough to test it on. For years, the first shelf got all the attention, because the collision story is intuitive and the culprit was right there. But the second shelf was never empty. And when Sikovi looked at the bullseye, at its 9 rings spaced in their particular pattern, and at that impossible outer ring speed that broke the collision clock, he did not see a galaxy that proved the collision theory. He saw a galaxy that might at long last be the one his own decades-old prediction had been waiting for. He saw the regular pattern of ring radii he had calculated all those years ago, not painted in light by spreading ripples, but pressed into the visible matter from underneath, by rings of something we have never seen. There was, however, still one more layer to the idea, the strangest layer of all, the one that takes it from unusual physics into something that sounds almost impossible. Because for the dark matter to behave this way, to fall and fold and hold these sharp-ringed shapes, it would have to be doing something that, until now, we have only ever seen happen in a laboratory, in a cloud of atoms chilled to within a whisper of the coldest temperature there is. Part 10. The condensate. There is a temperature below which matter stops behaving the way we expect, and strange new rules take over. We call the bottom of the temperature scale absolute zero, the coldest anything can ever be, the point where all the ordinary jostling and trembling of particles would, in principle, come to rest. Nothing in the universe is quite that cold, but in laboratories here on Earth, physicists have learned to chill small clouds of atoms to within a hair of it, a fraction of a degree above the absolute bottom. And when they do, something happens that has no equivalent in the warm, ordinary world. The atoms stop being separate individuals. They lose their distinctness and fall together into a single shared state, all of them occupying the same lowest rung of existence at once, behaving not as a crowd of many particles but as one coherent thing, a single quantum object spread across the whole cloud. This collective state has a name. It is called a Bose-Einstein condensate, named for the two physicists who predicted it long before anyone could make one, and it is one of the most genuinely bizarre things we have ever produced in a laboratory. Let me try to convey just how strange it is. In the ordinary world, things are individual. This grain of sand is distinct from that grain of sand. This atom is here, that atom is there, each with its own identity, its own position, its own motion. But in a Bose-Einstein condensate, that individuality dissolves. The particles overlap so completely that it stops making sense to ask which one is which. They share a single state, a single quantum description, and they move and respond as one unified whole. If you nudge one part, the whole thing answers, the way a single ripple runs across the surface of one continuous pool, rather than passing from one separate marble to the next. A condensate is, in a real sense, many particles that have agreed to become one particle, one smeared-out object obeying the underlying rules of the quantum world, not at the scale of a single atom, where we usually meet those rules, but at the scale of a whole visible cloud. On Earth, we make these clouds tiny, a wisp of atoms you could lose beneath a fingernail, held in place by lasers and magnetic fields, chilled with extraordinary care. They are delicate, fleeting, hard-won things. You might reasonably wonder how dark matter spread across a whole galaxy could ever be cold enough for this, when making a condensate on Earth requires chilling atoms to within a sliver of the absolute bottom of the temperature scale. The answer is one of the quiet gifts of cosmic history. Temperature at bottom is just motion, how fast things are jostling about, and the universe has been cooling for its entire existence. As the cosmos expanded over billions of years, everything in it stretched and slowed and grew colder, including whatever dark matter it contains. Axions in particular, if they formed in the way the theory describes, would have been born moving very slowly and would have only grown slower and cooler as the universe stretched around them. Until today they would be among the coldest, most sluggish things there are, drifting through the halos of galaxies at a relative crawl. So the deep chill that we have to manufacture with such effort in a laboratory, the universe may simply have provided for free by aging. The galaxy did not need lasers and magnetic traps to cool its dark matter. It only needed time, and time is the one thing the cosmos has in genuine abundance. And there is a strange comfort in that, when you think about it. The same long, patient cooling that turned the fiery young universe into the cold, quiet, star-strewn place we live in now would also be the thing that allowed its dark matter, if it is made of axions, to settle into these vast coherent states, to organize itself, to fold into the rings that one galaxy may be wearing. The order we might be glimpsing in the bullseye would be, in a sense, a product of cosmic old age, the universe growing calm enough, late enough in its life for its hidden substance to arrange itself into shapes. We tend to think of aging as a kind of running down, a loss of energy and possibility. But here perhaps the long cooling of everything is exactly what made a new kind of structure possible, a structure we could not have seen in the universe's hot and frantic youth. The dark matter had to grow old and cold before it could draw a ring. Now take that idea, that almost unbelievable laboratory curiosity, and let me ask you to stretch it to a size that the mind genuinely struggles to hold. The proposal on the table for the bullseye is that its dark matter, if it is made of axions, is not a warm scattered fog of separate particles at all. It is a Bose-Einstein condensate, the same kind of single, coherent quantum state that we make in a cold laboratory cloud, but spread not across a wisp beneath a fingernail, but across an entire galaxy. Axions are the right kind of particle for this. They belong to the family of particles that are allowed to pile into a shared state, and being so light and so cold, the leftover axions from the early universe could, in principle, settle into exactly this condition, all of them together forming one enormous quantum object filling the galaxy from edge to edge. I am going to ask you to do something difficult now, which is to actually try to picture this, even though it resists picturing. Let the whole bullseye fill your view, all 250,000 light-years of it, the great ring disk hanging in the dark. And now imagine that threaded through all of it, in and around and beyond the visible stars, there is a single thing. Not a crowd of countless separate dark particles, but one coherent quantum state, one continuous object the size of the entire galaxy, cold and silent and whole. The 9 rings of light that we can see, the rings of stars and gas that Hubble counted, become in this picture the visible hem of that single invisible garment, the places where the one great quantum thing has folded its caustics and pulled the ordinary matter into line. Stay inside that scale for just a moment before I let you back out, because it is one of the largest ideas I have ever asked you to hold, a single quantum object, the size of a galaxy. If it is real, it would be, without any competition whatsoever, the largest single quantum thing ever implicated in any observation in the history of science. Not in a laboratory, not under a fingernail, out there, more than 500 million light-years away, wearing 9 rings of starlight like the outline of something we were never supposed to be able to see. It helps, I think, to understand why axions in particular could do this when most things could not. The reason comes down to what kind of particle the axion is, and to a strange piece of quantum bookkeeping. Particles in the universe sort into 2 great families, distinguished by a rule about whether they are willing to share a quantum state. One family refuses. No 2 of them can ever occupy the same state at once, which is the very reason ordinary matter takes up space and does not all collapse into a point, the reason the chair holds you up. But the other family is gregarious. They are perfectly happy to pile into the same state, all of them together, in unlimited numbers. The particles that make up light belong to this sharing family, and so, it turns out, would axions. That willingness to share is the entire prerequisite for forming a Bose-Einstein condensate, for many becoming one. So an axion is not just light and shy and abundant. It is also, by its very nature, the kind of particle that can melt together with its fellows into a single coherent whole. Combine all of that, the feather lightness, the coldness of particles left over from the early universe, and stretched and chilled by billions of years of cosmic expansion, and the willingness to share a state, and you have the one ingredient that could, in principle, turn the invisible halo of a galaxy into a single enormous quantum object capable of holding sharp, ringed structure. Not every dark matter candidate could do this. The axion is special precisely because it could, and if it does, then the rings we see are not the dark matter itself, which remains as invisible as ever. They are its shadow cast in ordinary light. The dark matter folds into its caustic rings, and the gravity of those denser rings reaches out and gathers the gas and dust of the galaxy, pulling the ordinary matter into the same ringed pattern, compressing it until it ignites into stars. So we never actually see the dark matter. We see what its gravity has arranged the visible matter into. It is like discovering the shape of an invisible hand not by seeing the hand, but by watching the way it presses a sheet against itself, leaving the unmistakable outline of fingers in the fabric. The rings of light are the pressed fabric. The hand remains unseen, but the outline, if the idea is right, is real, and it is the outline of the thing that makes up most of the universe. I can feel how outlandish this sounds, and I want to honour that feeling rather than rush past it, because a healthy mind should balk a little here. A galaxy behaving as one quantum object is exactly the kind of claim that ought to make you raise an eyebrow, and the scientists proposing it know that. This is not established fact. It is a bold, specific, and genuinely strange hypothesis. But strangeness alone is not a reason to dismiss an idea, because the universe has repeatedly turned out to be far stranger than our comfort would prefer. The question is never whether an idea is strange. The question is whether it fits the evidence better than the alternatives, and so the real test, the moment everything has been building toward, is simple to state. We have the pattern that the caustic ring idea predicts, the specific spacing of rings that should appear if dark matter is doing this, and we have the actual measured spacing of the bullseye's 9 real rings, counted by Hubble and Keck. The only thing left to do is to lay one against the other and see whether they match. Everything depends on that comparison, so let us finally make it. Part 11. The Fit. Here is what Sikivi and Zhao did, stripped down to its essence. They took the pattern of ring radii that the caustic ring theory predicts, the regular sequence of distances at which rings of dark matter should fall if the infalling axions fold up the way the mathematics says they should. This was not a pattern they invented for the occasion. It was the same prediction Sikivi had published decades earlier, the spacing he had worked out long before the bullseye existed in any catalogue. And then they took the measured radii of the bullseye's 9 real rings, the actual distances from the centre, gathered by the great telescopes, and they laid the two side by side, the prediction made decades ago, against the galaxy found by accident a few years ago. And they reported that the rings of the bullseye fit the pattern. The spacing of the real rings lined up with the spacing that the caustic ring theory said dark matter should produce. Sit with what that would mean, if it holds. It would mean that the 9 rings we see, the rings of stars and glowing gas that make the bullseye look like a target, are not the marks of a collision at all. They would be the imprint, pressed into the ordinary visible matter, of rings of dark matter underneath. The infalling axion condensate, folding into its caustics, its sheets of higher density, would have reached out with its gravity and gathered the gas and dust of the galaxy into those same rings, gathered it densely enough to light up as stars. The dark matter would have been the mould, and the visible rings would be the cast. The starlight would be tracing, faithfully, the hidden shape of the invisible thing that was there all along. And in the words of the man who proposed it, the idea is precisely that the rings of the bullseye are an imprint of dark matter, caustic rings on the ordinary matter in the galaxy's disk. The rings you can see would be a portrait of the rings you cannot. I have been waiting all evening to say the next thing to you plainly, and I want to say it carefully, because it is the centre of everything. For nearly 100 years we have known dark matter only by its pull. We weighed it by how it tugged on spinning galaxies. We mapped it by how it bent passing light. We inferred it, deduced it, calculated it, felt it everywhere through the one sense it allows us, the sense of gravity. But we never saw its shape. We never looked at a picture and pointed and said, "There it is. That is what it looks like." Dark matter has always been the presence in the dark room, known by the way the furniture leans, never by the sight of its face. And what Sikivi and Zhao are suggesting, if they are right, is that the bullseye galaxy is the first place where we are not feeling dark matter's gravity, but looking at its form, that those 9 rings are the first portrait of the invisible, not its weight inferred, not its presence deduced, but its actual hidden architecture, drawn out in starlight clearly enough for a telescope to count, ring by ring by ring. The thing that makes up most of the universe, the thing we have never seen, perhaps seen at last, its shape stamped into the light of a galaxy more than 500 million light-years away. Let yourself feel, just for a moment, how long we have waited for a sight like that, even granting that it may not be real. For nearly a century, dark matter has been the great frustration of astronomy, a presence we could measure to remarkable precision and yet never lay eyes on. We have built entire careers, entire underground laboratories, entire telescopes around the goal of catching even a hint of it, and the universe has answered over and over with the same maddening reply. You can feel me, but you cannot see me. To inhabit a cosmos that is mostly made of something, and to be told by every direct experiment that you may not look at that something, is one of the strangest conditions our species has ever found itself in. It is the condition of living in a house and never being permitted to see the larger rooms. And so the mere suggestion, that one particular galaxy might at last be holding those larger rooms up to the light, drawing their outline for us in ordinary starlight, carries a weight that goes far beyond a single research result. It touches something close to longing. It is the possibility of finally seeing the face of the thing we have lived inside our whole existence and never once beheld. That is exactly why I have to keep pulling us back from getting carried away, even as I let us feel the pull of it. Longing is not evidence. Wanting something to be true, even wanting it for the best and most human of reasons, has misled more than a few brilliant people. The discipline of science exists precisely to protect us from believing the beautiful thing simply because it is beautiful. And so we hold both at once, the longing and the discipline, the hope that the dark has shown us its shape and the honest knowledge that we're not yet allowed to be certain. That tension, uncomfortable as it is the most truthful place to stand. It is the place the best scientists live all the time, holding a wondrous possibility in one hand and a healthy doubt in the other, refusing to drop either one. That is the moment the title of tonight's journey turns on. Most of the universe is made of something we have never seen, until now. And I have to hold those last two words, until now, with both hope and honesty at the same time, because they are doing something dangerous. They are promising a first sight of the invisible, and the truth is, we are not yet allowed to be sure. I told you at the very start that this was the other kind of story, the kind where the mystery seems to unsolve rather than solve, and here we are at the strangest crossing of it, where the unsolving has produced not a tidy new answer, but a staggering maybe. The fit is real. The pattern lines up. The collision clock genuinely is broken. The outer ring genuinely is in the wrong place for ripples. And the idea that explains it is beautiful and specific and built on decades of careful thought. But the dark matter it relies on is made of axions, and axions, as we stood beside one and watched it pass through everything untouched, have never been found. Not once. The whole magnificent structure, the caustics, the condensate, the galaxy-sized quantum object, the first portrait of the invisible, all of it rests on a particle we have searched for across decades and never caught. The fit is a fingerprint, but we have not yet confirmed whose hand made it. I want to be very careful with the word fit too, because it can be made to sound more conclusive than it is, and there is a subtlety here worth slowing down for. When two patterns match, it is genuinely strong evidence, but a match is not the same as a proof, because sometimes two different causes can produce patterns that look alike. The honest scientist always asks, could something else have produced this same fit by coincidence or by a different route? With the bullseye, that question is wide open. Perhaps the caustic ring pattern and the actual ring radii line up because dark matter really did draw them. Or perhaps the collision, in some more complicated form than the simple ripple picture, could also produce a similar spacing, and the apparent agreement with Sickevy's prediction is partly a happy accident. We do not yet know how to fully tell those possibilities apart from this one galaxy alone. One object, however remarkable, is a single data point, and a single data point can be the first member of a profound new pattern, or it can be a fluke that the next 10 galaxies fail to repeat. This is why the careful response to the bullseye is not celebration and not dismissal, but a kind of alert, patient watchfulness. A serious prediction has met a serious observation, and they have shaken hands, and that is exciting and real. But a handshake is the beginning of a conversation, not the end of one. What I find genuinely beautiful, though, is how little the wonder of this depends on which way it eventually breaks. Suppose, in the end, the careful work of the coming years shows that the collision model was right all along, that some richer version of the ripple picture can account for even the troublesome outer ring, and the dark matter reading falls away. Even then we would have learned something precious, because we would have been forced to look harder at a galaxy we thought we understood, and to test the limits of a theory we trusted, and that sharpening is how knowledge actually grows. And suppose instead the dark matter reading holds, and the axion is found, and the bullseye turns out to be the first of a whole family of galaxies wearing the visible imprint of the invisible. Then we would be living through one of the great moments in the history of science, the moment the dark first showed us its shape. Either outcome is worth the watching. The only response that would be wrong is the one that pretends we already know. So what do we do with a maybe this large? We do not pretend it is a yes, and we do not dismiss it as a no. We hold it, exactly as it is, with the wonder and the doubt in the same breath. Because here is the quiet truth that I think is worth more than any tidy answer. Whether or not the bullseye turns out to be the first sight of dark matter's shape, the very fact that a serious physicist can look at a famous galaxy, a galaxy everyone called solved, and propose with a straight face and a fitted pattern that its rings are the visible outline of the invisible majority of the universe, tells you how thin the line really is between what we have figured out and what we have only assumed. The discoverers saw a collision and a confirmed prediction. Sikivi saw a portrait of the dark, same 9 rings, same image, 2 entirely different universes of meaning, and an open question about which one we actually live in. And the honest position, the only honest position, is to stand in front of that image and admit that we are not yet sure which story is true. That is not a failure. That is what the edge of knowledge actually looks like, and it is a privilege to get to stand on it. Part 12. What the bullseye is pointing at. Let me gather the whole evening into one place, so you can hold both halves of it at once, the way the scientists now have to. On one side there is the collision, a little blue galaxy, an arrow, that punched straight through the centre of a giant about 50 million years ago, sending ripples of star formation spreading outward, and an old, respected theory of how such ripples behave that the bullseye's rings appeared to match almost perfectly. The discoverers of the galaxy stand on this side, and they have good reason too, because the culprit is right there, the gas trail points home, and the prediction fit. On the other side, there is the dark. The same 9 rings, but read not as ripples in gas, but as the imprint of caustic rings of dark matter, an axion condensate folding into a regular pattern that the visible matter then traces in starlight, an idea that explains the impossible speed of the outer ring and the strange sharpness of all of them, and that lines up with a prediction made decades before the galaxy was found. 2 stories, 1 image. And at this moment, in the year 2026, we do not know which is right. It would be easy to want me to break the tie for you, to tell you which one to believe, and I am not going to, because the honest answer is that the question is still open, and pretending otherwise would cheat you of the most valuable thing here, which is the chance to sit inside a real unsolved mystery rather than a packaged one. What I can tell you is that this will not stay open forever, because both stories make predictions, and predictions can be tested. If dark matter is made of axions, the experiments hunting for them, the patient silent detectors waiting underground, may one day catch one, and that single catch would transform the caustic ring idea from a beautiful possibility into something built on solid ground. And if the bullseye is the first of a family rather than a freak, then we should find more galaxies like it, more rings spaced in that telltale caustic pattern, as our telescopes grow sharper and our surveys grow wider. The discoverers themselves pointed to what is coming. A new space telescope soon to begin its work, designed to sweep enormous patches of sky that should turn up unusual objects like the bullseye far more readily than ever before. We will learn whether 9-ringed galaxies are one-in-a-universe accidents or a quiet recurring signature of something deeper. We will learn whether the pattern shows up again and again, and each new ringed galaxy we find will be another test, another chance for one of these 2 stories to pull ahead of the other. Until then, the bullseye hangs where it has always hung, more than 500 million light-years away, wearing its 9 rings, indifferent to our argument about what made them. And I find that I do not mind the not knowing. In fact, I have come to love it, because of what it does to that phrase we have been carrying since the very first minutes of tonight. A target nobody aimed at. We began there, with a galaxy found entirely by accident, a bullseye that no one was hunting, stumbled upon by a tired graduate student clicking through images in the quiet hours. It was a target that nobody aimed at. But look at what it may have become. If Sikivi is right, even partly right, then this accidental target, this thing we were never looking for, turns out to be pointing at the single largest hidden thing in all of existence. The bullseye is aimed, after all, not by us. It is aimed at the dark, at the invisible 85%, at the great unseen mass that holds every galaxy together and that we have spent a century feeling but never seeing. A target nobody aimed at, pointing straight at the thing we have most wanted to see and least been able to, and in a strange way pointing back at us, at our long blindness, at the fact that we have lived our whole history inside a universe whose larger part we have never once laid eyes on. There is a particular kind of patience that this moment asks of us, and I think it is worth naming because we are not very good at it. We live in a time that wants answers quickly, that treats not knowing as a problem to be solved by the end of the article. But the universe keeps its secrets on its own schedule, and some of the best questions take a generation or more to resolve, sometimes longer than the lifetime of the person who first asked them. Sikavi has carried his caustic ring idea for decades, waiting for a galaxy that might test it. The people listening for axions have spent their careers tuning the dial. The new telescopes that will find more galaxies like the bullseye are only beginning their work, and the verdict they deliver may not arrive for years. To care about a question like this is to accept that you may never personally see it settled, and to find that worth doing anyway, because the asking itself is a kind of participation in something far larger than any single life. We are not owed an answer on our timetable. We are only invited to look, and to wonder, and to hand the question forward. And what a question to hand forward. Not a small puzzle about one strange galaxy, but a thread that runs straight to the largest mystery there is. If those 9 rings really are the imprint of dark matter, then the next generation will inherit not just an answer about the bullseye, but a brand new way of seeing the invisible majority of the universe, a method for reading its hidden shape off the light of galaxies. And if they are not, if the collision wins, then the search for dark matter's face goes on, and somewhere out there is the galaxy, not yet found, that will finally show it to us, the way the bullseye was found, by accident, by attention, by someone slowing down long enough to notice a target nobody had aimed at. Either way, the looking continues. Either way, the dark is still out there, still mostly unseen, still waiting. Think about where that leaves us. You and me, sitting here tonight under our own sky, inside our own galaxy, which is itself mostly made of this same unseen thing. The dark matter the bullseye may be showing us the shape of is not exotic and far away. It is here. It is around us right now, threaded through the Milky Way, streaming through this room, passing through your body as you rest. The same invisible majority that, on the other side of an enormous gulf of space, may have drawn 9 rings of light around a distant giant. We are not observers standing outside this mystery, peering in at someone else's strangeness. We are inside it. We are made of the small, visible fraction, the 5% that shines, floating in the great dark remainder that does not. And for the whole of human history, we have been unable to see the larger part of our own home. The bullseye offers the possibility, only the possibility, that the larger part has finally, in one place far away, allowed itself to be seen. So here is where I will leave you, with the question rather than the answer, the way I promised. Most of the universe is made of something we have never seen. That has been true for as long as there have been minds to wonder about it, true in every dark room of the cosmos, true above your head tonight. And out there, hanging in the patient dark, a galaxy nobody was looking for wears 9 rings of light that may, or may not, be the first true portrait of that invisible majority, the first time the dark has shown us its shape instead of merely its weight. We do not yet know if it is real. We know only that it might be, and that the test is coming, and that for now we get to stand in the rare and beautiful uncertainty of a thing not yet decided. Until now, the universe kept the larger half of itself hidden. Perhaps it still does. Or perhaps in one accidental bullseye more than 500 million light-years away, it has quietly begun to let us look. Either way, the next time you stand under a dark sky and feel how much is out there, remember that most of what you're looking into is something no one has ever seen, leaning on us all in the dark, holding the bright things in place, waiting, maybe, in its own slow time, to be found.